Okay. Okay. So um, we talked it was maybe a week ago about you have access to this handout under MATLAB assignments where MATLAB assignment number 2 is. This handout's here. And the handout, the part you want to focus on is the role of interchanges. Okay. And we talked about this system where, like, what we're used to doing as humans is in a column, we're used to using the smallest number, usually it's a 1. We're used to using the smallest number as a pivot to get zeros in below the number, to row reduce the matrix. And in this case, we took 40,000, negative 40,000 times the first row and added it to the second row. And when we did that, uh, if we consider round off error uh, to like nearest 4 significant digits, then if we were to use that, and that of course our computers are much better than that, but nevertheless they have round off error. If we did that, if we did row reduction that way, the solution we would get is that x2 equals 1 and x1 equals 0. And of course, the true answer to the solution is much closer to 1, 1. Okay. As a matter of fact, they give, well, that's what the true answer is, very close to 1, 1. But if we interchange the row, if we interchange the two equations and move the second equation to the make it the so what I'm trying to talk, like LU factorization in section 2.5, you had no row interchanges. But if you allow row interchanges, which is what they're doing here, you move the second equation, make it the first equation, and then what you're going to do is multiply the first equation to get a 0 in this spot here in front of x1. You're going to multiply the 1 by negative 25 millionths. And there'll still be some precision lost, but when you solve the system, you're going to get the solution 1, 1, which isn't exactly right, but it's very close to the right answer. And the right answer, I gave that, if you look at the recording for I recorded when we talked about this handout, I recorded the exact answer. So we have a very the lesson of this handout is that computers, it's very good for them to use the largest value in a column as a pivot. Not the smallest value like we do, but they use the largest value. So that means that row interchanges are necessary for computers to do these to solve the systems efficiently with the least amount of round off error. Then we have to, if we're going to do LU factorization on a computer, we have to incorporate row interchanges into our algorithm. Section 2.5, the way you solved the LU factorization, you did not incorporate any row changes. But we need to incorporate row interchanges in order to help us with the round off error. And this is what a focus is of MATLAB assignment number 2. MATLAB assignment number 2, you're going to be using MATLAB to do your LU factorization. But the LU factorization in MATLAB is not going to be the same as what you would get as what you would do if you use section 2.5 LU factorization without the row interchanges. So, and again, you may have to, so Matthew experienced that firsthand. All right. So that being said, I have a second handout here that I want to talk about. So I don't think you necessarily need to copy this example down. Just follow along with me. Don't copy the example down. It'll be in the recording. what we're doing here, and I like every discussion that I do to be connected to a section. Well, partial pivoting was mentioned on page 17 in section 1.2. After you learned about row reduction, it talked about how computers use partial pivoting. Again, partial pivoting is when you use the largest value in a column to produce zeros in that column. So we want to find what's called permuted LU factorization for this matrix A, where we use partial pivoting. Then we're going to use the resulting equation. It's not A equals L times U. It's going to be P times A equals L to U. P times A equals L times U, where P is a permutation matrix. We're going to use that to help us find the determinant of A. So let me show you how this is going to work. Okay, and again, you can listen to the recording again as you wish. So what I've done is I have the matrix A here. Okay, the matrix A is right here. It's a 3 by 3. And what I want to do is I want to move the 4 here in the first column to the 4. I want to move to the top of the column. So when you do row operations, when you do the forward face of the row operations, you take multiples of the first row and add it to the second row and third row to produce zeros. But if I'm going to use the biggest number in the first column as my pivot, as a computer would do, it would be the 4. Well, to move the 4 to the spot where the 1 is, I have to do a row switch. I have to do a row switch. And the row switch is taking E1, that's an elementary matrix, right? That's, taking the identity matrix and switching the first and third columns. You multiply E1 by A, and that's going to get you the matrix 4, 8, 4, 2, 3, negative 1, 1, 4, 4. So, we're happy about that because now the 4 is located in the top spot of the column. Okay, the 4 is located in the top spot of the column. All right. But what I'm going to do now is I want to actually then that product there, that product matrix, the E1 times A, I'm going to multiply that by another matrix, E2, another elementary matrix. And E2 is the matrix where we switch the effect of multiplying E2 by E1A is E2 is the elementary matrix where you switch the second and third rows. So if you multiply E2 by that product matrix E1A, you're gonna switch the second and third rows. Okay, and MATLAB is going to do LU factorization on this matrix. But why did we do that? Why did we multiply by another matrix E2? When we did E1 times A, we moved the pivot 4 into the top spot in the first column. But you now have to think about the second column. In the second column, you have an 8, 3, 4. But you're not worried about the 8 when you do the row operations to get the matrix in echelon form. You're worried about the 3 and the 4. Okay, well, what's the largest number between 3 and 4? It's going to be the 4. So you want to move the 4 into the second row and move the 3 down to the bottom row. Okay, and when you do that, and that's why you have to multiply E1A by E2. So you have 2 row switching matrices that put this matrix in the best possible form to reduce round-off error. The pivot 4 is in the first row. The first column, the pivot 4 is at the top, and in the second column. Okay, and the pivot 4 is great. In the first column, the pivot 4 is greater than the numbers below it, 1 and 2. In the second column, the pivot 4 is greater than the numbers below it, greater than the 3. So MATLAB is going to do LU factorization on this matrix. Okay, that's what MATLAB does the LU factorization on. And when you do MATLAB, when you do LU factorization in MATLAB, it's gonna generate a matrix L, a matrix U, and a matrix P. The matrix P is called your permutation matrix. The permutation matrix is going to be the product of your row switching matrices that you needed to use to get the matrix A in the correct form for the LU factorization that MATLAB does. And again, that correct form makes sure that that in the first column, the largest number is at the top, so it can be used as a pivot for the first column. And in the second column, the largest number is, well, in this case, in the second spot. Okay, so it can be used as a pivot for the three below it. This is what partial pivoting. So this is the this is what you're doing. So like I said, it differs from LU factorization in the textbook, but for MATLAB assignment number 2, it's very important. It's you have to understand it so that you understand when you run MATLAB code for LU factorization, you can see what it's doing. Now, let me just mention here, we have here now that P times A equals L times U. P times A equals L times U. P is the permutation matrix, and P times A equals L times U. That's permuted LU factorization. Okay, so how can we get a formula for the determinant? Well, of course, we're going to take the determinant of both sides. So the determinant of P times A equals the determinant of L times U. But then the determinant of a product of two matrices is the product of the determinants. So the determinant of P times A is the determinant of P times the determinant of A. The determinant of L times U is the determinant of L times the determinant of U. But what is L? L is a lower unit triangular matrix, right? So the determinant of L is going to be 1, right? So that's easy. That's easy on the right side. That's easy. The U is going to be in echelon form. So the determinant of U is just going to be the product of the values on the diagonal, because we're dealing with square matrices here. Now on the left, the determinant of P in front of the determinant of A is going to be equal to -1 squared. Because we use two row interchanges, the determinant of P is going to be -1 squared. Okay, so that's how the determinant of P, that permutation matrix, is going to be either 1 or -1. And from your knowledge about rules for determinants, how do you get the matrix P? Well, you're doing row interchanges, right? So we did two row interchanges. So the determinant is going to be. I want to be a little bit careful here. One moment. Let me just make sure one thing. Yeah, the determinant of P will equal -1 to the power, and the power is equal to the number of row switches that you did. Okay, and so you take the let me see here. Yeah, that's how it's going to work. Because look, the determinant of E1 is just one row switch, right? So that's going to, the determinant of E1 would be -1. But then you're multiplying it by the determinant of E2. But E2, I'm not saying this the right way. To get the elementary matrix E1, you took the identity, okay, and the determinant of the identity is 1, but you did a row switch on it. So the determinant of E1 would be -1 times 1. The determinant of E2, you took the identity and you made a row switch. You switched the second and third rows. So the determinant of the identity is 1, but because you did the row switch, you have -1 times 1. And this is why the determinant of P is -1 squared. And by the way, the general formula would be the determinant of the permutation matrix is -1 to the rth power. Okay, and so where R is the number of row interchanges. And if you go into section 2.5 and I'm sorry, section 3.2, if you go to page 173, look at Formula 1. Look at Formula 1 there, and you'll see the connection. So now we want to solve for the determinant of A. The determinant of A equals the determinant of U divided by -1 squared. Okay, but you can write that then, you know, as the determinant of A equals -1 squared times the determinant of U. And so now you have a very easy way to compute the determinant of a matrix A very quickly. And it could be the -1 squared, that computer can do that fast. And the determinant of U is just the product of values along the diagonal. So this is what, when you look at MATLAB assignment 2, at like where they talk about you know, they talk about this kind of thing. This is where it's coming from. And what we'll do in the next class is so basically this discussion of partial pivoting is going to be broken up into 3 little discussions. This was the second discussion. What we'll do on next Thursday in class is I'll do an LU factorization in MATLAB with you so that you can see. I mean, we'll do actually the LU factorization in MATLAB for this very example, but you can do it on your own if you want, and you'll see that you'll see what I'm talking about. You know, in terms of you know, what gets generated. I thank you for staying a few minutes after class. Let me stop the recording.